let's talk about peer-to-peer network. So in peer-to-peer network, so there is no one specific machine providing services. All the machines or the hosts are participating. The hosts are providing at the same level. They're providing services to each other, right? It's self-scalable, like we'll see in a minute, right? And the popular examples of peer-to-peer applications are file distribution, such as BitTorrent application, and streaming, Kanban, and then voice over IP. Like Skype is also Skype is also a peer-to-peer application, right? So before we talk about a specific peer-to-peer application that is BitTorrent, let's quickly talk about and let's try to compare the peer-to-peer application and client-server applications, right? So the question that we want to answer in order to understand these two or compare these two types of application is how much time it requires to distribute a file having a size F, right, from one server to n peers, both in client server architecture and then peer-to-peer type of applications. So in order to understand, let's understand the knowledges that are the notations that we are using here. So here, this US sub F is server's sending rate, right? Is the rate at which the server is sending data to a host, okay? And this server has a file having size F, clear? And now, similarly, this D sub I is the download capacity of a host, and similarly, U sub I is the upload capacity or the sending capacity of a host. Okay, so these are the notations that we'll be using. So it's important for us to understand these notations. So first is the U sub S. This is the rate at which a server is sending a file to host. F is the size of the file that we want to download. And similarly, if we talk about a host, D sub I is the download rate of a host, and U sub I is the upload rate of a host, the rate at which a host can upload the. And let's assume that there is no bandwidth constraint here. The network bandwidth is in abundance, right? So there is no issue of the network bandwidth, and then still we'll see how we can have a problem in client server environment here, right? So if these notations are clear, if I talk about distributing a file in a client server environment, then the server transmission must sequentially send or upload n copies. For example, if there is one host trying to access the copy of the file, the server will send this copy to one host, then it will send this copy to the second, and then the third, and the n number of hosts. So the question is how much time it takes to send one copy of the host to one host, since it's sending sequentially. So the number one question is, what is the time required to send one copy of the file? That is very simple. We will divide the size of the file by the sending rate of the server. Remember, F is the size of the file, right? And this is what? This is the upload capacity or the sending rate of the server, right? So if I want to send one copy of the file to a host, how much time it will take? I will divide the size of the file by the sending rate of the server. But now, if there are n number of hosts and want to have the copy of the same file, how much time it will take to send n copies? That is n number of copies divided by the sending rate of the server, which is the same u sub s, right? So similarly, if we talk about the time required by a client to download a copy of the file, so that is what we know, this that the min is the minimum client download rate, right? The download rate of a client, and how much time it will take by a client to download a file, the size of the file divided by the download rate of the client. So if I talk about the time to distribute a file to end clients using client server architecture, so this is what, this is the distribution of a file in a client server environment. So it's greater than equal to maximum of these two. What is this? Time required to distribute n copies of a file. Yes, no? Yes. And what is this? File size divided by the download rate of a client. Time required to download a file by a client. Download the file by a. So the distribution time required in a client server environment is basically maximum equals to or greater than maximum of these two. What it is, the time required to distribute n copies of a file, or the time required to download a file by a client, whichever is higher. So what do you think, if this n is increasing? I mean, if I have to send n number of copies, which time will be more? Obviously, the time to distribute n copies of a file. So what I'm saying here is that if n increases linearly, there is a linear increase in n. What is happening here? I mean, we are maybe increasing here. So we are increasing here what? The number of hosts. So, so what this is doing? This is increasing n linearly, right? But what about this? The sending rate of the server is the same, right? So this means what? This will take more time to transfer a copy of the file if if I keep on increasing the number of clients requesting the same, file. N is increasing, the N is increasing here. So in this scenario, the N is increasing, but there is no increase in the upload capacity of the server. So this means it's not scalable. Means if I add more number of clients and they are requesting the copy of the same file, this will increase the file distribution time in a client server environment or scenario. So that's why. So if I want to scale it up, what I have to do then? What do you think? What we have to do? I have to add more servers here. More servers here, right? Only then, the time can be to transmit a file can be reduced. Otherwise, not self-scalable. It's not scalable, right? Okay, but now let's compare the file distribution time in a peer-to-peer environment. And again, here we are familiar with this. The time to send one copy is what? The time to send one copy is the size of the file divided by the sending rate of a server or a machine, or a server, say in this case. A server is there, let's assume, right? And we are also familiar with this time. That is what the minimum time required to download a copy of the same file by a client. But if all these clients are taking part and sharing the copy of the same file, then what is happening? Now, I'm assuming a scenario where every client is having a copy of the same file, or a chunk of the same file. And now all these clients are not only sending or downloading the copies, but also sending the chunks of sharing the chunks of the same file with the other clients as well. So what will be the distribution time in a peer-to-peer network? It would be maximum or equal to or greater than the maximum of these three. I mean, what is this? This is the time to send a copy of the file by the server. This is the time to send what? Or time to download a copy of the file by a client. What is this? This is the time to download n copies of the file. And now see what is happening here. The max upload rate is what? Is the upload rate or the sending rate of a machine plus the total number of machines that are participating in this process. So if this n is increasing, I mean, if there are more number of hosts requesting for the same file, right? But this UI is also increasing. Why? Because all these hosts are now also participating in this sending receiving process. These are all not only downloading the files, but these hosts are also uploading the files to the other machines or the other clients. So if there is a linear increase in n, there is also linear increase in the sending capacity service or sending capacity of the network also. So this is how this, if I add more number of devices, this will self-scale the system in a peer-to-peer arrangement. Why? Because all the peers are participating in this sending receiving process here. Clear? And let's try to understand this with the help of this with this example, this chart, right? So on x-axis we have the number of nodes, right? 5, 10, 15, so on and so forth. And here we have the minimum distribution time. And here we have a line representing the time required to distribute a file in a client-server environment, and the time required to distribute a file in the peer-to-peer arrangement. So look at the graph of client-server environment. As the number of nodes are increasing, the time to distribute a file is also increasing linearly. Why? Remember, it was sending n number of copies of a file divided by the upload capacity of the server. So if the number of nodes are increasing, the n is increasing. So the time to distribute the file is also increasing. So if n is increasing, it was 5, 10, 15, 20. So there is a linear increase in the time required for the distribution of the file. But on the other hand, look at the graph of, in peer-to-peer arrangement. If the number of files or the number of nodes are increasing, the time to distribute the file is decreasing. Why? Because now this n is not only increasing, but also we have what? We have all the nodes contributing in this sending receiving process. If this n is increasing, the number of nodes sending or sharing the copy of the file is also increasing. So clearly, the time required to distribute a file in a peer-to-peer arrangement is less, or it decreases as the number of nodes are increasing. But on the other side, in a client-server environment, if the number of files or the number of nodes are increasing, there is an increase in the file distribution time. So the peer-to-peer networks are or the applications are self-scalable. Right. So let's quickly talk about peer-to-peer application such as BitTorrent, see how it works. So BitTorrent is a file distribution application, right? So in a BitTorrent like application, we have a torrent that is basically the collection of all the peers participating in the file distribution. So torrent is what is a group of peers participating in the file distribution, and then we have a we have a tracker. Tracker is basically a server that is tracking, or you can say it's an infrastructure node uh, for each that is tracking each torrent, right? So every time peer participate in the distribution of a file, it registers itself with the tracker or this infrastructure node, right? And then we have a chunk. Chunk is basically the size of a chunk of a file is 256 kilobyte, right? This is 256 kilobytes. I should have. Okay, and let's see how it operates. So let's assume that Alice arrives in the system and she wants to access a certain file. So what she does is that it obtains a list of the peers participating in the file sharing in a specific file sharing process that we call a torrent, right? So what happens is that this tracker provides Alice a list of the peers participating in the exchange of a particular file. So initially, 50 nodes are or 50 peers details are forwarded to the Alice, right? And Alice start exchanging the files with these peers, right? And what Alice does is it keeps calculating its transfer rate with all of its peer every 10 seconds. So Alice, after every 10 seconds, recalculates or calculates its sending rate or receiving rate with all the peers, right? And Alice, identify the 4 top peers that she has the highest ascending rate. And after every 30 seconds, Alice, picks another additional neighbor and again calculates its ascending rate with that peer. So peer joining the torrent, if, for example, as we have the case in this example, Alice just arrived and she has nothing to share, but she can get a list of the torrents, and over the time she can participate in this file sharing process, right? So while downloading a peer, also uploads chunks to the other peer, right? So it's a trading algorithm. So uh, peer may change peers with whom it exchange. How? We'll see in a minute in the next slide. So a peer can come and go, right? Or you can just download a file, or you can disconnect from the internet, or you can exit the application, close the application selfishly, or you can selflessly keep on participating in this process. So at any given time, there are different peers that have different subsets of files. Alice, first of all, request for the rarest file chunk first. So this is important. So, for example, there are 50 peers participating in the file sharing process. Every peer has a certain chunk of the file, but Alice would request first the rarest chunks from the participating or from the peers that she's interacting with, right? So Alice selects what? The 4 peers here. Alice selects the 4 peer. How? Because these are the peers that have the highest, sending rate. Their sending rate is highest. Okay, and it recalculates the top 4 after every 10 seconds. Alice recalculates its top 4 providers, and after every 30 seconds, Alice optimistically unchoke. Optimistically unchoke means hoping that the other peer will also share the chunks with the Alice. So what I'm saying is that after every 30 seconds, Alice will unchoke, say, another peer, optimistically unchoke another peer, say Bob, hoping that Bob will be one of its 4 top providers, right? And Alice start sending data, and Bob say reciprocates and also sends data at a highest rate and becomes one of the top 4 providers of Alice, right? And in a similar way, Alice, after every 30 seconds, or Bob after every 30 seconds, keep on optimistically unchoking another, peer to find if it is one of the 4 best provider of Alice or Bob. So in this way, in this application, a peer keeps on changing its top 4 providers and keep on getting the chunks of the files.